The closest star to our sun is just 4.24 light years away. That word, just, is the most misleading word in all of astronomy, because 4.24 light years isn't close. It's 25 trillion miles of nothing, a distance so extreme that even the fastest human-made object ever built would take tens of thousands of years to get there. Civilizations rise and collapse in less time than that journey would take. And that's before you even face the real problem, because getting there is only the beginning. Out in interstellar space, there is no protection. Radiation strong enough to tear apart DNA. Microscopic particles that hit with the force of explosions. Engines that can accelerate, but may never have enough fuel to slow down. And a life support system that doesn't just need to work for years. It needs to work longer than recorded human history. And which leads to a terrifying possibility. Maybe the barrier isn't technology. Maybe the universe itself is telling us something. Maybe the stars were never meant to be reached. And then, in 2016, everything changed. At a press conference held by the European Southern Observatory, scientists announced something that made that impossible distance suddenly feel personal. Orbiting Proxima Centauri, they had found a planet, a rocky world, roughly the mass of Earth, sitting in the narrow region where liquid water could exist. They named it Proxima Centauri B, the nearest potentially habitable world ever discovered, which changes the question completely. Because now it's not just, can we reach the stars? It's, what happens if we don't? There is something about the night sky that has always made humans stop. Yeah, you could be walking somewhere, in a hurry, with things to do, and then you look up, and something about the darkness between the stars makes the hurry feel very small. Scientists have a word for the distance to those stars. They call it light years. And that phrase sounds almost comfortable, like something manageable. A light year. A year of light. Not that far, right? But a light year is not a year at all. It's a distance. The distance that light travels in an entire year, moving at 186,000 miles every single second. 1 light year is about 5.88 trillion miles. And Proxima Centauri, our nearest stellar neighbor, the closest star to our own sun, sits 4.24 of those light years away. Which means, to reach it, you would have to travel across 25 trillion miles of absolute, cold, silent nothingness. Just the void. Yes, and yet when people talk about interstellar travel, this is the star they always mention first, because it feels like the logical starting point, the nearest rung on a ladder that might eventually reach every star in the galaxy. And for most of human history, it was just a number, a fascinating, humbling number that sat in textbooks and documentaries like a piece of very heavy furniture, impressive to look at, but impossible to move. Then in 2016, that number became something else entirely. It became an address. Scientists found a planet orbiting Proxima Centauri, a rocky world, roughly Earth-sized, sitting at just the right distance from its star that liquid water could theoretically pool on its surface. They called it Proxima Centauri B, and overnight, those 25 trillion miles stopped being just an abstract measurement. They became a hallway between us and something that might be alive. And that changes everything about how you think about this question. Because before that discovery, asking whether humans could reach the nearest star was mostly an intellectual exercise. A fascinating puzzle about physics and engineering, something that engineers and physicists debate over coffee. But after 2016, the question became something closer to urgent, because now there's a destination, a specific place, a world sitting there in the darkness, 25 trillion miles away, that might have oceans, that might have weather, that might have, in the quiet way that simple molecules sometimes arrange themselves into something breathing and replicating and reaching upward, life. And we can't get to it, not even close to close. And that gap, that enormous, that almost insult to the imagination gap between where we are and where we want to go, is what this story is really about. So let's begin at the beginning. Not with the planet, and not with the rockets, but with the distance itself. Because until you really understand what 4.24 light years means, not as a number, but as a lived experience, as a physical reality, Nothing else in this story makes proper sense. And to understand it, you have to let go of the way human beings normally think about distance. Because our brains are not built for this. Humans are, at our core, walking creatures. We evolved on a planet where the longest distance any of our ancestors ever needed to cross on foot was maybe a few thousand miles. The whole history of human migration, the expansion across continents, the settling of every corner of Earth, all of it happened at the speed of walking, maybe a few miles per hour, occasionally on horseback, which got you up to maybe 30. And even as technology extended our reach, boats, trains, cars, planes, the mental model stayed roughly the same. Distance is something you cross. It takes time, but not that much time. A few hours by plane gets you almost anywhere on the planet. A few months by ship, in the old days, got you across oceans. Even driving across the entire continental United States takes less than a week. Distance, for humans, has always been a problem that yielded eventually. A thing you could cross if you kept going long enough. Space doesn't work like that. Space operates at scales that don't care about human willpower or human technology or human ingenuity. Now, if the moon is about 239,000 miles away, that's the farthest any human being has ever traveled from Earth. It takes about 3 days to get there. 3 days. That sounds manageable. You pack a bag, you launch, you drift through the void for 3 days, and you arrive. 12 people have done it. They walked on the surface, collected rocks, looked back at the Earth hanging small and blue in the black, and then came home. 3 days there. 3 days back. 6 days total for the most extreme journey in human history. And then you look at Proxima Centauri, the closest star, and it is 4.25 light years away, which, to put it in units that actually mean something, is about 268,770 times the distance from Earth to the Sun. Or, and if you prefer, you would have to travel to the moon and back roughly 52 billion times to cover the same distance. 52 billion round trips to the moon, just to reach the nearest star. Let that settle for a moment. Just breathe and let that number sit there. And the uncomfortable truth is that no matter how clever we get with our units or our metaphors, the human brain simply cannot process numbers that large. We understand them intellectually, the way you can understand that a certain molecule is 0.000000003 meters wide without actually being able to picture it. The numbers are there. The comprehension is not. And the scientists and engineers who work on this problem know this. They live with this gap every day, this yawning distance between what the numbers say and what the mind can hold. So they've developed tricks and little thought experiments designed to make the scale feel real, at least for a moment. Here's one of them. Take the entire solar system, not just Earth and the moon, but everything. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter with its enormous storms and its 95 moons, Saturn with its rings, Uranus, Neptune, and the long, cold dark beyond Neptune where Pluto wanders and the scattered disk begins and the slow, far-reaching influence of the sun finally starts to fade. Shrink all of that down. Compress the entire solar system into a circle about the size of a large dinner plate, maybe 12 inches across. At that scale, Proxima Centauri, our nearest neighbor, our cosmic next-door star, would be sitting about 430 feet away. Not on the table, not in the same room, out the door, down the hallway, and around the corner. You wouldn't even be able to see it from where you're standing at the dinner plate that is our solar system. And that's just the nearest star. There are over 400 billion stars in the Milky Way. At that same scale, the galaxy as a whole would be roughly the size of North America. This is the scale of things, and it is not a scale that invites confidence. Now, to be fair to the optimists, and there are some very serious, very smart optimists working on this problem, distance alone isn't the whole story. Distance is just a number. What matters is what technology can do about it. And the history of technology is, in many ways, the history of making distances shrink. A journey that once took months began taking weeks, then days, then hours. Speeds that would have seemed magical to someone living a century ago are now routine. We have sent robotic spacecraft across the solar system and received photographs from the moons of Jupiter and the storms of Neptune. We have landed on Mars not once but many times, sending small-wheeled explorers to crawl across its rust-colored surface and send data back across hundreds of millions of miles. If the story of technology is the story of shrinking distances, then maybe interstellar travel is just the next shrinkage, just the next problem that eventually yields. But here's where things get quiet and a little uncomfortable. Because when you actually look at the numbers, not the inspiring headlines, but the actual physics, there's a pattern that becomes very hard to ignore. And the pattern is this. The jump from planetary travel to interstellar travel is not a gradual increase in difficulty. And it's not climbing a steep hill that eventually levels off. It's a cliff, a near vertical wall of physics and energy and time that is qualitatively different from anything humanity has encountered before. Not bigger, not just harder, different in kind. Let's talk about Voyager 1. This spacecraft was launched in 1977, and it is, as of this moment, the farthest human-made object from Earth. It crossed the boundary of the solar system, the heliopause, where the sun's influence ends and interstellar space begins, somewhere around 2012. It is now drifting through the interstellar medium, that cold, sparse region between the stars, moving at about 38,000 miles per hour, which is extraordinarily fast by any human measure. A car moving at 38,000 miles per hour would cross the continental United States in about 4 minutes. It is a rocket ship built in the 1970s, traveling at a speed that a fighter pilot can barely imagine. And yet, at that speed, Voyager 1 would need roughly 73,000 years to reach Proxima Centauri. Not 73 years, not 7,300 years, 73,000 years. Agriculture was invented about 12,000 years ago. Writing is about 5,000 years old. The Egyptian pyramids are about 4,500 years old. Voyager's journey to the nearest star would take 6 times longer than all of recorded human history, beginning to end. And Voyager 1 isn't even pointed at Proxima Centauri. It's heading in a completely different direction. But even if it were, 73,000 years. The same civilization that built and launched that probe would need to exist, continuously and unbroken, for 73,000 years to receive the data it gathered on arrival. To put that in perspective, modern humans, Homo sapiens, people who looked and thought like us, have only existed for somewhere between 200,000 and 300,000 years total. Our entire species history is only about 3 to 4 times the length of that hypothetical journey. A journey that a probe moving at 38,000 miles per hour would need. The Parker Solar Probe, launched in 2018, is the fastest human-made object ever created. At its fastest point, it moves at about 430,000 miles per hour, which feels impossibly fast. It circles the sun in a matter of weeks. And at that speed, a journey to Proxima Centauri would take about 6,700 years. Still longer than all of recorded human civilization. Still longer than the time between ancient Sumeria and now. And still moving nowhere near fast enough. So what would actually be needed? What speed would make the journey even vaguely feasible within a human lifetime, or even within a few generations? This is where the engineers and physicists start doing math that feels increasingly like science fiction, but is actually just physics. To complete the trip in a human lifetime, say around 80 to 100 years, you would need to travel at somewhere between 5 and 10% of the speed of light. At 10% of light speed, the journey takes about 42 years. At 5%, about 85 years. That's the ballpark. Those are the target speeds. And to reach those speeds, the energy required is breathtaking. Kinetic energy scales with the square of velocity. This is a simple physics relationship, but its implications are profound when you're thinking about interstellar travel. If you double your speed, you need 4 times as much energy. Triple your speed, 9 times the energy. And we're not talking about doubling or tripling. We're talking about going from the fastest thing we've ever built, which moves at about 0.046% of the speed of light, to 5 or 10% of the speed of light. That's an increase in speed of roughly 100 to 200 times. And because kinetic energy scales with the square of velocity, you'd need not 100 or 200 times more energy, but something on the order of 10,000 to 40,000 times more energy. For a spacecraft of any useful size, the numbers involved are comparable to decades of Earth's total global energy production, not global energy consumption in a year, in decades, all of it, focused on one spacecraft. That's the energy price of admission. And then there is the rocket equation. And the rocket equation is one of those beautiful, terrible pieces of mathematics that engineers encounter early in their careers and never fully recover from. It was derived in 1903 by Konstantin Tsiolkovsky, a Russian schoolteacher who spent his evenings thinking about rocketry and his days watching his students struggle with arithmetic. The equation describes a simple relationship. To change a rocket's velocity by any given amount, you need a certain ratio of fuel mass to final, empty, mass. And the cruel twist of the equation is this. The fuel needed grows exponentially with the desired change in velocity. Linearly won't cut it, exponentially, which means that as you want to go faster and faster, the amount of fuel required doesn't just increase, it explodes. For a rocket trying to reach even 10% of the speed of light using conventional chemical propulsion, the math produces a fuel-to-payload ratio that is, in the most literal sense of the word, astronomical. You would need to launch something like 1 billion times the mass in fuel for every unit of payload you want to deliver, 8 billion to 1. Which means if you want to land even a kilogram of scientific equipment on a planet orbiting Proxima Centauri using chemical rockets, you would need to start with something on the order of 1 billion kilograms of fuel. That's more than the total mass of every rocket ever launched in human history, combined. Just for 1 kilogram of cargo, just to one star, just the nearest one. This is why chemical rockets, for all their power and their history and their genuine heroism, the Saturn V, and the Falcon Heavy, the entire lineage of fire and thunder machines that humanity has built over the past century, are simply not the answer to interstellar travel. Not because they're bad technology. They're magnificent technology. They're just the wrong tool for a problem of this scale. Using chemical rockets for interstellar travel is a little like trying to dig a tunnel from New York to London using a teaspoon. You might technically be moving in the right direction, but the tool and the task are so mismatched that the effort barely registers as progress. So if not chemical rockets, then what? This is where the thinking gets both more exciting and more sobering in equal measure, because there are ideas, genuinely creative, scientifically grounded ideas, for propulsion systems that could theoretically reach the speeds required. And each one of them, when you look closely, reveals a new layer of difficulty, a new reason why the problem remains stubbornly, almost insultingly hard. Nuclear pulse propulsion is perhaps the oldest and most straightforward of the serious proposals. The concept dates back to the 1950s and was the subject of a real, classified United States government program called Project Orion. The idea is almost charmingly brutal. You build a large plate at the back of your spacecraft, and you explode nuclear bombs behind it, one after another, using the shockwave of each explosion to push the spacecraft forward. It works. The physics genuinely works. Studies showed that an Orion-type spacecraft could theoretically reach speeds of around 3 to 10% of the speed of light, which puts interstellar travel in the realm of decades rather than millennia. And the mathematics, unlike chemical propulsion, don't immediately dissolve into absurdity. An Orion spacecraft would need thousands or possibly millions of nuclear pulses over the course of its acceleration phase. But the fuel-to-payload ratios are at least not in the billions to 1 territory. But nuclear pulse propulsion requires actual nuclear weapons, detonating inside or immediately behind the spacecraft at regular intervals. The engineering challenges are severe. The radiation shielding required for the crew would add enormous mass. The impact plate at the back of the ship would be subjected to repeated nuclear explosions, and would need to be both extraordinarily strong and radiation resistant. The shock absorbers connecting the plate to the rest of the spacecraft would be some of the most demanding mechanical components ever designed. And there is, of course, the political problem. The 1963 Partial Test Ban Treaty prohibits nuclear explosions in space. Building an Orion spacecraft would require either renegotiating or abandoning that treaty, which was itself a landmark of Cold War diplomacy, and launching thousands of nuclear warheads on top of a rocket from Earth's surface introduces a risk profile that makes most space agencies deeply uncomfortable. Nuclear fusion propulsion is in many ways a more elegant approach. Instead of detonating discrete bombs, a fusion drive would use controlled nuclear fusion reactions, the same process that powers the sun, to generate an exhaust stream of high-velocity particles that pushes the spacecraft forward. The specific impulse of a fusion drive, a measure of how efficiently a propulsion system converts fuel into thrust, would be vastly superior to any chemical rocket, and potentially competitive with nuclear pulse propulsion. Some designs, like the Daedalus concept studied in the 1970s by the British Interplanetary Society, suggested that a fusion-powered spacecraft could reach about 12% of the speed of light, bringing the travel time to Proxima Centauri down to around 36 years. There is, however, a rather significant problem with fusion propulsion. We don't have fusion power, not on Earth and certainly not in space. Controlled nuclear fusion has been the perpetually imminent promise of energy research for about 70 years. The running joke among physicists is that commercial fusion power has been 20 years away for the past 6 decades. There has been genuine progress. The National Ignition Facility in California achieved ignition in 2022, actually getting more energy out of a fusion reaction than was put into the lasers that triggered it. But the gap between a controlled laboratory reaction and a compact, reliable spacecraft engine is enormous. The engineering complexity of a space-ready fusion drive, one that can sustain continuous reactions for decades while surviving the stresses of space travel, makes the Manhattan Project look like a high school science fair. Antimatter propulsion takes the idea even further. In theory, matter-antimatter annihilation is the most efficient energy release process in the universe. When a particle of matter meets its antimatter counterpart, say a proton meets an antiproton, they annihilate completely, converting their entire mass into energy according to Einstein's equation E equals mc squared. This is not an approximation or an estimate. It is complete, total conversion of mass into energy. Nothing in physics beats it for efficiency. An antimatter drive, in theory, could accelerate a spacecraft to a significant fraction of the speed of light with a relatively small amount of fuel. The exhaust velocity would be extraordinary. The specific impulse would be off the charts. It would be, if it worked, the perfect rocket engine. But humanity has produced approximately a few nanograms of antimatter in total, ever. In all the particle accelerators on Earth since the first antiparticle was created in a laboratory, a nanogram is 1/1,000,000th of a gram. A gram of table salt contains more atoms than the number of antiprotons ever created by human technology, and a practical antimatter drive would require grams or possibly kilograms of antimatter, depending on the mission. At current production rates, gathering enough antimatter for even a modest interstellar probe would take longer than the universe has existed, and that assumes the production rate doesn't change, which of course it would with investment. But the orders of magnitude involved make this a challenge measured not in decades but in centuries, and possibly much longer. There is also the storage problem. Antimatter by definition annihilates on contact with ordinary matter. You cannot put it in a box. Any conventional container would be destroyed the moment the antimatter touched the walls. Storing it requires either magnetic containment, holding charged antiparticles in a magnetic field that keeps them away from any material surface, or some form of neutral antimatter, like antihydrogen, which doesn't respond to magnetic fields and is even harder to work with. The engineering of an antimatter storage system that is reliable, compact, lightweight, and failure-safe over decades of operation is so far beyond current technology that it is difficult to discuss without the language becoming almost hypothetical. And then there is the idea that most clearly captures both the ingenuity and the painful limitations of human thinking on this problem: Breakthrough Starshot. Announced in 2016, the same year as the discovery of Proxima Centauri b, which is probably not a coincidence, Breakthrough Starshot was a genuinely serious, generously funded initiative to send a spacecraft to Alpha Centauri the star system that contains Proxima Centauri. The plan was developed by some of the most respected physicists and engineers in the world, backed by hundreds of millions of dollars, and it represented perhaps the most realistic proposal for actual interstellar travel that has ever been put forward. And the way it solved the problem is, in hindsight, almost heartbreaking in its cleverness. It gave up on everything. The plan stripped the spacecraft down to almost nothing. Not a crewed vessel, not even a conventional robotic probe, but a tiny chip. A postage stamp-sized piece of electronics with a camera, a communication system, and a sail. The whole thing would weigh about a gram. And rather than carrying its own fuel, which is where all previous proposals collapsed under the weight of the rocket equation, Breakthrough Starshot would use an external energy source to push it. A massive array of ground-based lasers, perhaps the size of a large building, would focus an enormous beam of light on the tiny sail. The pressure of the light would accelerate the chip to about 20% of the speed of light in a matter of minutes. At that speed, the chip would arrive at Proxima Centauri in about 20 years. It would take photographs, measure the magnetic field, maybe detect the atmosphere of Proxima b, and then send the data back. A tiny probe traveling to another star and returning scientific data in about 40 years total, for the first time. Our interstellar travel seemed not just theoretical but actually imaginable. And then you look at the details. The laser array would need to produce about 100 gigawatts of power simultaneously, roughly equal to the output of about 100 large nuclear power plants, all focused on a single point in the sky. The chip itself would need to survive the sudden acceleration without being destroyed. Going from 0 to 20% of light speed in a matter of minutes subjects it to forces that would shred any conventional material. The sail would need to reflect the laser beam almost perfectly, because even a tiny fraction of absorption would melt it instantly. The chip would need to navigate autonomously for 20 years through the interstellar medium, maintaining its trajectory without any real-time communication from Earth. On arrival, it would have only a few hours to gather data before the Proxima system was behind it, because it would be moving too fast to stop or orbit, and the data it gathered would need to be transmitted back from 4 light-years away by something the size of a postage stamp, using a transmitter drawing power from a tiny photovoltaic sail. That data, transmitted at the speed of light, would still take 4 years to reach Earth. None of these problems are technically impossible, in the sense that no known law of physics absolutely prevents them from being solved. But none of them have been solved. As of today, Breakthrough Starshot remains exactly what it was when announced, a plan. A very detailed, very serious, very well-funded plan. But the prototype chip has not been flown. The laser array does not exist. Yet the materials for the sail have not been developed. The project has done valuable research and published genuine science, but the gap between the concept and a functioning mission is still measured in decades of engineering work, possibly more. And this was the stripped-down version. The one that gave up a crew, gave up size, gave up the ability to stop or orbit or explore in any meaningful depth. This was the absolute minimum viable interstellar mission, and it is still profoundly beyond current capability. Let's step back from the engineering for a moment and think about something a little more human. Think about what it would actually feel like to be inside one of these proposed missions. Not the chip, the human one. The kind that would actually need to send people. Imagine you are on a spacecraft. You've been traveling for 2 years. The sun, which was a brilliant point of light behind you for the first few months, is now just the brightest star in a sky full of stars. You can still see it, but it doesn't feel like home anymore. The Earth itself, if you were to point a powerful telescope at our solar system, would be invisible. Too small, too dim, lost in the glare of our own sun. Everything you have ever known, every person, every city, every ocean and mountain and field and memory, exists somewhere in that faint dot of light behind you. And ahead, 4.24 light-years away, is another dot of light, smaller, redder, dimmer, and you have years left to go. Many years. The human dimensions of an interstellar journey are, in some ways, more daunting than the engineering ones, because engines can be designed and tested and improved. Yes, materials can be developed and refined, but human beings are not engineering problems. They are something much more complicated. And the deep history of long-term confinement and isolation, from Antarctic expeditions to submarine deployments to the International Space Station, points toward a consistent and troubling pattern. Extended isolation does things to people. Not catastrophic things necessarily, not usually, but quiet, cumulative things. Erosions of mood and motivation and social cohesion. Irritabilities that calcify into conflicts. The sense of purpose that drove a mission in its opening weeks, gradually wearing thin under months and years of routine and boredom, and the particular loneliness of being cut off from the normal rhythms of human life, the International Space Station. Yet our most extensive experience with long-term spaceflight typically houses crews of 6 or 7 people. The longest any single human being has spent in space continuously is about 437 days, set by a Russian cosmonaut in the 1990s, and more recently approached by Scott Kelly and Christina Koch in separate missions. And these missions, impressive as they are, take place with a view of Earth filling half the sky, with real-time communication with family and friends and mission control, with regular resupply missions bringing fresh food and spare parts and mail from home, with the psychological anchor of knowing that if something goes seriously wrong, a medical emergency, a critical system failure, a rescue mission is not impossible. In interstellar space, none of those anchors exist, and communication with Earth would be delayed by years in each direction. A message sent from the spacecraft would take 4.24 years to arrive at Earth. The reply would take another 4.24 years to come back. So anything the crew communicates to mission control, any question, any request, any distress signal, would receive an answer nearly 9 years later. For all practical purposes, the crew would be on their own, completely on their own, in a way that no human mission has ever been before. The nearest humans would not be 8 months away, as on a Mars mission. They would be literally years away, and there would be no way to get to them, because the spacecraft would be moving at a significant fraction of the speed of light, and there would be nothing following behind it. There is a particular kind of silence that astronauts describe when they first float to the window of the International Space Station and look down at Earth. Not the silence of the spacecraft itself. These things are surprisingly loud, full of fans and pumps and the constant mechanical noise of life support systems working. But the silence of the recognition, of understanding, at some gut level deeper than thought, that you are very, very far from everything. That the thin blue atmosphere visible at the edge of the planet is all that stands between the surface and the void you're now floating in. That you are, in a very real sense, the farthest from home that your personal biology has ever been in all its evolutionary history. This feeling has been described by astronauts from dozens of countries and backgrounds, and in dozens of different ways. Some find it peaceful. Some find it terrifying. Some oscillate between the two in a matter of minutes. Practically all of them say it changes something. That coming home, they see the Earth differently, more fragile, more precious, more miraculous. Now extend that feeling across decades. Not a 6-month mission, not a year. Decades. The entire span of a person's productive adult life, spent in a metal cylinder, surrounded by a crew of perhaps a dozen or 24 people, with no possibility of going home, no possibility of going anywhere, no view of Earth at all. Just the stars, which in deep space look even harder and colder than they do from the surface. The crew would age aboard the ship. They would have birthdays and anniversaries and illnesses and moments of grief. They would form relationships and break them and form new ones. They would probably have children. If the mission were multi-generational, they would watch crewmates die. They would deal with conflict and grievance and the slow, grinding tedium of days that are all roughly the same. And they would know, with a certainty that few humans in history have had to face, that they would never see Earth again. Never smell a forest or feel rain or hear the particular noise of a city or the particular silence of an open field. Never be surrounded by more than a few dozen human faces for the rest of their lives. The psychological research on this is genuinely sobering. Studies of Antarctic overwinter crews, small groups isolated in a hostile environment for months, unable to leave, show patterns of psychological deterioration that seem almost inevitable above a certain duration. There is a phenomenon called the third quarter effect, in which morale and psychological health tend to plummet around the 3/4 mark of a long mission, when the end is still far enough away to feel unreal but close enough to count. There is the steady erosion of what psychologists call social density, the sense of richness and variety that comes from interacting with different people in different contexts. On a spacecraft, you see the same faces day after day in the same spaces. There is nowhere to go for solitude and nowhere to go for stimulation. The spacecraft is everything. And research shows that this kind of isolation, not just from other people, but from variety, from novelty, and from the full spectrum of human experience, takes a measurable toll on cognitive function, emotional regulation, and mental health. None of this means that humans couldn't adapt. Humans are extraordinarily adaptable. The history of exploration is full of people who endured conditions that should have broken them and didn't. Antarctic explorers survived winters in near-total darkness, in conditions of cold and privation that would be unimaginable to most people today, and came back changed but whole. The early submariners spent months underwater in vessels with no fresh air and no natural light, and no real connection to the surface world. And they did it again and again. There is a capacity in the human spirit for endurance that consistently surprises even the scientists who study it. But those historical examples all had something that an interstellar mission wouldn't have. The knowledge that there was a world to come back to. That the ordeal was finite. That somewhere, at the end of the darkness, there was a surface to return to, a family to hug, a meal to eat in the presence of people who had not been in the same room with you for months. The interstellar crew would have no such knowledge. For them, there is no returning. There is only forward. And then there is the body. The physical human body, which evolved on a planet with a specific gravity, a specific atmosphere, a specific magnetic field, a specific level of radiation, and a specific cadence of light and dark that regulates everything from sleep to hormone levels to mood. The human body did not evolve for space, it evolved for Earth. And the evidence from decades of spaceflight shows, in increasingly detailed and uncomfortable ways, exactly what space does to a body when it's removed from everything it was built for. The most immediate and dramatic effect is the loss of bone density and muscle mass that occurs in microgravity. Without gravity to push against, the body decides that bone and muscle are unnecessary metabolic luxuries and starts reducing them. Astronauts on the International Space Station lose about 1 to 2% of their bone density per month. Over a 6-month mission, that adds up to 6 to 12%, a loss that takes years to fully recover, even with intensive exercise and physical therapy. On a multi-decade interstellar journey, even with artificial gravity generated by spinning the spacecraft, the effects on the musculoskeletal system would accumulate in ways that are still not well understood. Artificial gravity helps, but the engineering cost, in terms of spacecraft size, mass, and complexity, of generating Earth-like gravity through rotation is substantial. The cardiovascular system also changes in space, in ways that are still being actively studied. Without the need to pump blood upward against gravity, the heart becomes more spherical and slightly smaller. Blood shifts toward the upper body, which contributes to the stuffy head, puffy face appearance that astronauts often develop in microgravity, and also puts the cardiovascular system under unusual stresses. Some astronauts return from long missions with measurable decreases in cardiovascular fitness that persist for months. But the fluid shift upward in the body also affects vision. A significant fraction of astronauts develop visual changes during long missions, caused by increased intracranial pressure, pressing on the optic nerve. Some of these changes are permanent. Several American astronauts have returned from long ISS missions with permanently altered vision, a finding that alarmed researchers because it suggests a potentially serious and lasting neurological effect of extended spaceflight. And then there is radiation. This is perhaps the single most intractable biological challenge of deep space travel, and it deserves careful attention because it is so often underplayed in popular descriptions of space exploration. Earth's surface is protected from the full force of cosmic radiation by two things: the planet's magnetic field, which deflects charged particles, and the atmosphere, which absorbs them. Together, these two layers reduce the radiation exposure at sea level to about 2 to 3 millisieverts per year, well within the range of safe biological tolerance. In low Earth orbit, where the ISS operates, the magnetic field still provides partial protection. Astronauts there receive about 150 millisieverts per year, which is the established limit for career astronaut exposure. But on a mission beyond Earth's magnetic field, to the Moon, to Mars, or to the stars, the radiation environment changes dramatically. Cosmic rays, high-energy particles that come from supernova explosions and other violent events throughout the galaxy, stream through the solar system continuously. They pass through most materials easily, including conventional radiation shielding. Unlike the particles in a hospital X-ray, which can be blocked by a lead apron, cosmic ray particles are so energetic that they punch straight through steel, through aluminum, through water, through human tissue, and through almost anything you might try to use as a shield. In the process, they can break DNA strands, ionize molecules and cells, trigger mutations, and, if the exposure is high enough and sustained enough, initiate cancer or damage the central nervous system. Astronauts on a 6-month Mars transit mission would receive a radiation dose that roughly triples their lifetime cancer risk. On a 40-year mission to Proxima Centauri, the cumulative exposure would be severe enough to raise very serious questions about whether the crew could survive it, let alone arrive in condition to do useful work. There are ideas for radiation protection. Water makes a reasonable shield against some types of radiation. Polyethylene, a common plastic, is surprisingly effective because of its high hydrogen content. Superconducting magnetic fields, essentially a spacecraft surrounded by its own artificial magnetic field, could deflect charged particles the way Earth's magnetic field does, though the engineering involved is formidable, and the field would need to be quite powerful to provide meaningful protection. But the fundamental problem remains. Cosmic radiation in deep space is of a kind that conventional shielding strategies handle poorly, and the mass required to provide adequate protection using passive shielding would be enormous, adding to the already crushing weight requirements of the spacecraft. Let's talk for a moment about something that might seem obvious but is worth really dwelling on: the concept of closed-loop life support. Everything a human needs to survive — oxygen, water, food, the removal of carbon dioxide, and other metabolic waste products — must either be brought from Earth or produced on board. For short missions, this is relatively straightforward. The Apollo lunar missions carried everything they needed for a week. The ISS resupply ships bring fresh water, food, and replacement equipment on a regular schedule. But for a mission that takes decades, the concept of bringing everything from Earth becomes untenable. The mass of food and water and oxygen required to keep even a small crew alive for 40 years would exceed the structural capacity of any spacecraft we could plausibly launch. And the solution is recycling, complete, almost perfectly closed-loop recycling of everything. Water reclaimed from urine, sweat, and condensation. Oxygen produced by plants or by chemical reactions from reclaimed carbon dioxide. Food grown aboard the ship using hydroponics or some other form of cultivation. Everything that the crew produces, every exhaled molecule, every drop of urine, every gram of metabolic waste, must be captured and processed and returned to the cycle. Nothing can be lost, nothing can be vented, nothing can accumulate. The loop must be essentially closed, meaning that the efficiency of recycling must approach 100%, maintained continuously, without failure, for decades. We do not currently have this technology. The ISS life support system is impressive, and it does recycle a significant fraction of the water aboard the station. But it still depends on regular resupply from Earth for consumables, spare parts, and replacement components. There are regular failures, pumps that break, filters that clog, systems that need maintenance and repair. And these failures are managed because resupply missions are possible, and because the station itself is in constant communication with mission control, which can troubleshoot problems in real time with a full team of expert engineers. An interstellar spacecraft cannot rely on any of these safety nets. Every component that could fail must either not fail or be repaired by the crew on board. Every consumable must be regenerated. Every system must be self-sustaining. There is an experiment that attempted, in a much more modest way, to explore what closed-loop life support looks like in practice. Biosphere 2, built in the Arizona desert in the late 1980s, was a sealed artificial ecosystem covering about 1.3 hectares, designed to test whether a small group of people could survive entirely on the food and air produced within the sealed environment. The project was extraordinarily ambitious and genuinely pioneering. 8 crew members, called Biospherians, were sealed inside in September 1991, and within months, things began to go wrong. Oxygen levels fell as microbes in the soil consumed it faster than the plants could replenish it. The crew began experiencing altitude sickness symptoms from the thin air. Morning glories, an invasive species, took over large sections of the agricultural area, reducing food production. Cockroaches and ants thrived while native species struggled. The crew was hungry for most of their time inside, losing significant body weight. The scientists were forced to bring in additional oxygen from outside to prevent dangerously low levels. The experiment, in a certain sense, failed. Not catastrophically. The crew survived. But the dream of a perfectly self-sustaining sealed biosphere was revealed to be far more complex, far more fragile, and far less predictable than the designers had imagined. And Biosphere 2 was sitting in the Arizona desert, with sunlight, with a large diverse ecosystem, with a full team of outside scientists monitoring everything, with the ability to open the door if things got truly dangerous. An interstellar spacecraft would have none of those advantages, and it would need to not fail for 40 years. Food deserves its own moment of attention. Not because it's the most dramatic challenge, it isn't, but because it is so profoundly human, and because the relationship between food and morale and psychological health is something that tends to get lost in the technical discussions about propulsion and radiation shielding. Food is not just fuel, it is culture, it is comfort. It is one of the primary ways that human beings mark time and celebrate and grieve and come together. The importance of food to human well-being extends far beyond its caloric content, and on a spacecraft, food is one of the few remaining connections to a life that existed before the mission. The crew of an interstellar spacecraft would be eating whatever the ship can grow, cooked in whatever ways the ship's facilities allow, for decades, yet with no variation that isn't planned and engineered in advance. Current spacecraft nutrition is a triumph of food science. NASA's food scientists have developed meals that are nutritionally complete, relatively palatable, and long-lasting. But astronauts consistently describe food quality as a major factor in their psychological well-being in space, and a major source of frustration when it isn't right. The food on the ISS is better than it used to be, but it is still highly processed, highly standardized, and limited in variety. Astronauts dream about fresh fruit and vegetables. They talk about the meals they'll eat when they get home with a fervor that is almost poignant. And those astronauts are in space for 6 months, not 40 years. The interstellar crew would need to grow their own food. This sounds almost bucolic, a spacecraft with little gardens and fields of grain. But growing food in space is a deeply complex engineering and agricultural challenge. Plants need light, which requires powerful artificial lighting systems that consume significant electrical power. They need water, another closed-loop system that must be maintained perfectly. They need the right temperature, the right atmosphere, the right nutrients. They are susceptible to fungal infections and insect pests and diseases that can spread rapidly in the enclosed environment of a spacecraft. A single plant pathogen that escapes into the ship's agricultural area could devastate the crop and leave the crew without food. And growing enough food for a multi-person crew for decades requires a significant area, certainly more than most proposed spacecraft designs easily accommodate. Then there's the medical dimension of food. The crew's nutritional needs will change over time. People age differently. Some crew members may develop conditions that require specific dietary management. The relationship between nutrition and long-term health is enormously complex, and the idea of providing optimal nutrition to a diverse crew over decades, using only what the ship can produce, is a challenge that makes clinical nutritionists genuinely uncomfortable. Now, there is something else, something that is discussed in quiet corners of the astrophysics and ethics community, but rarely makes it into the mainstream conversation about interstellar travel. It's because it is so deeply uncomfortable that most people prefer not to think about it too hard. It is the question of what happens when the journey takes longer than a single lifetime. Because even with the best propulsion technologies we can imagine, a mission to Proxima Centauri would take decades. And decades is a long time. Long enough that crew members might grow old and die during the voyage. Long enough that the mission might need to be passed from one generation to the next. And long enough that the children born on board, children who never chose this life, who never signed up for the mission, who never set foot on Earth, would be asked to carry it forward on behalf of people who are now dead, and a planet that exists only in stories and recordings and the fading memories of the oldest crew members. Hey, this is the generation ship problem. The idea of a spacecraft carrying human beings across interstellar distances over multiple generations has been explored in science fiction for nearly a century. It is one of the most haunting concepts in the genre, and the reason it haunts is not the engineering. The reason it haunts is the ethics. You cannot get consent from a person who doesn't yet exist. The children born on a generation ship would have no choice about their circumstances. They would be born into a mission they did not choose, in an enclosed environment they cannot leave, on a journey that will last their entire lives, to a destination they will never experience as children but might or might not survive to see as elderly adults. They would live and work and struggle and love and die on a spacecraft, defined entirely by a mission that their grandparents or great-grandparents had chosen. This is, at a minimum, a profound ethical question. And at a maximum, it is something that reasonable people might consider deeply wrong. There are philosophers who argue that the generation ship scenario is essentially a form of forced servitude, that breeding human beings specifically to serve a particular purpose in an environment they cannot leave is incompatible with human dignity. There are others who argue that it is not fundamentally different from the circumstances many humans throughout history have been born into, that none of us choose the family or the country or the time period we're born into, and that the generation ship crew would at least be serving a noble purpose. The debate is genuinely open and genuinely difficult, and it doesn't resolve neatly. There is also the practical problem of what happens to a community over multiple generations of extreme confinement. Human social systems require a certain minimum complexity to function stably. Small groups isolated from the broader currents of human culture tend to evolve in unusual directions, developing their own dialects, their own customs, their own hierarchies and rules. This is not inherently bad. It is simply what human communities do. But on an interstellar ship, where there is no way to import culture, no way to bring in new people or new ideas, and no way to escape the social structures that develop, the community might drift in directions that are not conducive to mission success. Cults have arisen in smaller communities with more freedom. How totalitarian impulses emerge in communities under stress, and 3 or 4 generations into the voyage, the people on board might have a very different relationship to the original mission, and the original values, and the original purpose, than the people who set out. Some researchers have suggested that a minimum population size of about 160 to 200 people would be needed to maintain genetic and social diversity over multiple generations of interstellar travel. Enough to prevent inbreeding, enough to sustain a functioning social structure, enough to ensure that critical skills are passed down through generations. Other, more conservative estimates put the number much higher, in the thousands. Either way, the mass and resource requirements of a spacecraft carrying hundreds or thousands of people for decades are staggering, and the complexity of the social management problem, ensuring that this community remains functional, motivated, and capable across multiple generations, is beyond anything that has ever been attempted. There is an idea that seems, on first hearing, like it solves this problem elegantly. It's called suspended animation, or more scientifically, torpor. The idea is simple. Instead of having the crew live out decades of normal life during the voyage, you induce a deep, hibernation-like state that slows the body's metabolism to a tiny fraction of its normal rate. The crew sleeps through the journey. They don't age significantly. They don't eat much. They don't need entertainment or social interaction or psychological management. When they wake up at the destination, They're more or less the same people who went to sleep at departure. Problem solved. Except that we cannot do this. Not really. Not yet. Not even close to the level needed. There are techniques in medicine for cooling the human body and inducing a sort of emergency hibernation. Therapeutic hypothermia, used in cardiac surgery and severe brain injury cases, can slow metabolism significantly for hours, sometimes up to 12 to 24 hours in experimental settings. Some animals hibernate for months, their metabolism slowing to a few percent of their normal rates, their body temperature dropping to just above freezing. Bears don't fully hibernate but enter a state of torpor where their metabolism drops by 50 to 60%. Certain small mammals, like ground squirrels, are genuine hibernators, with core body temperatures approaching freezing and heart rates dropping to just a few beats per minute. Studying them, scientists have found biochemical mechanisms that protect their cells from the damage that would otherwise occur during such extreme metabolic depression. But humans are not ground squirrels. The mechanisms that allow small mammals to hibernate safely involve complex genetic and biochemical adaptations that humans simply don't have. Attempting to chill a human body to hibernation temperatures without these protective mechanisms causes ice crystal formation inside cells, damage to the cardiovascular system, and other serious injuries. There is ongoing research into whether some of the biochemical pathways of animal hibernation could be replicated pharmacologically in humans, triggered by drugs or genetic modification rather than evolved biology. Some of this research is genuinely interesting, and there have been tantalizing hints of progress. But even the most optimistic researchers in this field talk in terms of decades of development before human torpor could be safe and reliable for periods of months, let alone years. And an interstellar mission at current best-case speeds would require decades of torpor, not months. The gap between what the biology requires and what we currently can deliver is very large. The silence of deep space has a particular quality to it that is hard to describe without having experienced it, or at least imagined it vividly. Not the silence of a quiet room or a remote forest, where the absence of sound still allows for the presence of a world. This is the silence of the void. A silence that exists not because nothing is making noise, but because there is nothing there to make noise, and nothing there to hear it. In interstellar space, between the stars, the density of matter approaches what physicists call a hard vacuum. A few atoms per cubic meter, mostly hydrogen. No air, no medium for sound to travel through. If the spacecraft's hull failed, there would be no explosion, no roar, just the sudden, silent escape of air into a space that is essentially nothing. The psychological weight of that silence, of that absolute and non-negotiable emptiness in every direction, is difficult to prepare for. We know this from the reports of astronauts who have been outside the ISS on spacewalks, floating in the vacuum with only a visor between them and the void. Several have described profound experiences of both wonder and fear, a vertiginous awareness of how thin the boundary is between life and the vacuum, how completely alone they are even a few feet from the spacecraft. Now extend that to years, decades. The void doesn't change, it stays void. The stars don't get closer, not in any way the eye can detect for most of the journey. The crew wakes up each day and the windows show the same stars in roughly the same positions, the slight changes in stellar positions detectable only with instruments. For years, the landscape never changes because there is no landscape. There are only stars, and the growing distance behind them, and the unimaginably long distance still ahead. Humans need novelty. We need variation. Change, the sense of things moving and evolving and happening. Evolution shaped us for a world of constant change, changing seasons, changing terrain, changing social dynamics, changing challenges. But put a human in an environment with no change, and the mind creates its own changes, which may or may not be healthy ones. Boredom, in its deepest form, is a kind of suffering, and the interstellar voyage might be the most boring journey in the history of the universe. In the most literal sense of the word, hours and days that are identical to the hours and days before them, stretching into months and years of the same view, the same people, the same routines, with the knowledge that there is no escape and no end visible on any human timescale. There is a thought experiment that sometimes comes up in these discussions that I find oddly moving. It goes like this. Imagine you are a member of the crew of an interstellar spacecraft. Somewhere in the middle years of the journey, you've been in space for 20 years. The Earth is so far behind you that it is invisible, even in your most powerful telescope. You cannot see it, you cannot feel it. You know it's there, because the instruments say it's there, because the data says it's there, because the mission logs say it's there. But experientially, existentially, the Earth is gone. You cannot hear voices in real time. The messages from home are years old when they arrive. The people who sent them may have changed significantly, or aged significantly, or some of them may have died in the years between sending and receiving. You are not on Earth anymore, in any meaningful sense. You are not anywhere. You are in transit, in the long, black, empty transit between two distant suns. And you will be there, in that transit, for the rest of your life. What do you hold on to? What keeps the mission real? What makes tomorrow feel different from yesterday, when yesterday and tomorrow look exactly the same? This is not a question with an engineering answer. It is not a problem that a better engine or a bigger spacecraft or a more efficient life support system can solve. It is a human question, and the honest answer is that nobody knows. The psychological research on long-duration confinement gives us data about what goes wrong over months and years. It does not give us confidence about what would sustain a person or a community over decades. History provides examples of remarkable human endurance, but they are almost all examples of people enduring hardship while still in sight of a return, still connected to a world. The interstellar crew would not be. Some people, thinking about this problem, land on a kind of peace with it. Yet they suggest that the crew would develop a culture so rich, so complete in itself, so purposeful in its mission, that the absence of Earth would gradually stop being a loss and become simply a different kind of life. That the children born on board would not grieve the Earth they never knew, because you cannot miss what you've never had. That the community would find meaning and joy and beauty in the stars, and in each other, and in the astonishing, unprecedented nature of what they were doing. This is a hopeful reading, and it's not impossible, but it requires a degree of psychological engineering, a careful, deliberate cultivation of culture and meaning and social structure that we have never attempted at this scale and never successfully completed in any analogous setting. Others land somewhere darker. They suggest that the psychological and social demands of the interstellar voyage would exceed human tolerance, that the community would fragment or deteriorate or produce outcomes that the original planners would not recognize and might not endorse, that the mission, however noble its origins, would produce suffering on a scale that is difficult to justify, that the stars, for all their beauty and significance, might not be worth that cost. This too is not impossible. History has given us examples of exploratory expeditions that began with noble purpose and ended in tragedy, in mutiny, in violence, in the death of everyone involved. And those expeditions lasted months, not decades, had technology that could, at least in theory, get the survivors home. Faced dangers that were extreme, but ultimately of a kind that human biology had some evolutionary preparation for. Let me tell you something about Proxima Centauri b, the planet itself. Not the journey to it, not the engineering of reaching it, but the thing itself sitting out there in the dark, 4 light years away, receiving the reddish light of its dim star. Proxima Centauri is a red dwarf. This means it is smaller, cooler, and dimmer than our sun. Much dimmer. Only about 0.15% as luminous as the sun. A tiny dim coal of a star that has been burning, slowly and steadily, for a very long time. Red dwarfs are remarkable in one sense. They live almost forever, at least on astronomical timescales. Yet while the sun will burn for about another 5 billion years before expanding into a red giant and eventually cooling into a white dwarf, Proxima Centauri will burn for approximately 4 trillion years. That's 4,000 billion years, in a universe that is currently only about 13.8 billion years old. Proxima Centauri will still be quietly shining long after every other star in the galaxy has gone dark. In this sense, it is perhaps the most durable real estate in the local universe. But the dimness of Proxima Centauri creates an immediate problem for Proxima b. For the planet to receive enough warmth to maintain liquid water, to be in what astronomers call the habitable zone, it has to orbit very close to its star. Very close. Proxima b orbits at about 5% of the distance between Earth and the Sun. For comparison, Mercury, the closest planet to our Sun in a hellish, heavily cratered world, orbits at about 39% of the Earth-Sun distance. Proxima b is far closer to its star than Mercury is to ours. And this extreme proximity creates a set of challenges that significantly complicate the picture of a habitable world. The most important is tidal locking. At such close distances, the gravitational force of the star is powerful enough to lock the planet's rotation to its orbital period, the same way the moon's rotation is locked to Earth, which is why we always see the same side of the moon. A tidally locked planet shows the same face to its star permanently. One side is in eternal day, bathed in continuous starlight, hot and dry. The other side is in eternal night, cold and dark. There may be a narrow strip, a twilight band around the edge, where conditions are more moderate, where you might find liquid water pooled in the perpetual dim light. But the classic picture of a blue and white world with oceans and continents and weather patterns regulated by the cycle of day and night is unlikely. The climate of a tidally locked world would be strange and extreme in ways we can barely model. And then there are the flares. Proxima Centauri is a flare star. Red dwarfs, for all their durability, are not gentle. They periodically emit enormous blasts of radiation. Solar flares vastly more powerful, relative to the star's normal output, than anything our own sun typically produces. During a major flare, the X-ray and ultraviolet radiation reaching Proxima b could be thousands of times the normal level. And without a strong magnetic field and a substantial atmosphere to absorb this radiation, these flares would strip away any atmosphere the planet might have developed and bombard the surface with lethal levels of radiation. Whether Proxima b has such protection, whether it has a magnetic field, whether it has retained an atmosphere, is something we genuinely don't know. The planet was discovered through the radial velocity method, which detects the gravitational tug of a planet on its star. It tells us the planet is there, approximately how massive it is, and how far from the star it orbits. It does not tell us anything about the atmosphere, the surface, the magnetic field, or the chemistry. Whether Proxima b is a world with oceans and perhaps even life, or a bare, radiation-scoured rock with no atmosphere, that is a question that current telescopes cannot answer. And it is one of the most important questions in all of science. There are ongoing efforts to learn more. Space telescopes designed for atmospheric characterization, including the James Webb Space Telescope, can, under the right circumstances, detect the spectral signatures of gases in the atmospheres of planets orbiting other stars. As these capabilities improve, we may eventually get a first glimpse of whether Proxima b has an atmosphere, and if so, what it contains. The presence of certain combinations of gases, oxygen and methane together for instance, which would rapidly react with each other and disappear without some process constantly replenishing them, would be a powerful suggestion of biological activity. But Proxima b's edge on orbit relative to its star means we can't use the transit method to study its atmosphere, which significantly limits our options. Learning the truth about Proxima b from Earth's vicinity is going to be a slow and indirect process. And knowing the truth, completely and confidently, would almost certainly require actually going there. This brings us to something important that sometimes gets lost in the engineering discussions and the biology discussions and the ethics discussions. The reason why this all matters, the reason why the question of interstellar travel is not just a fascinating intellectual puzzle, but something that touches something very deep and very serious about the human condition, and possibly about the long-term future of life itself. Astronomers and astrophysicists who study the deep future of the cosmos have worked out, in broad strokes, what the future of Earth looks like. The Sun, currently about 4.6 billion years old, is slowly brightening as it ages. Over the next billion or so years, the amount of solar energy reaching Earth will increase by about 10%. This sounds modest, but its effects on climate and habitability are potentially severe. Models suggest that within about a billion years, a period almost incomprehensibly long but bounded, the runaway greenhouse effect on Earth will begin, making the surface progressively less habitable until, several billion years from now, the oceans boil away entirely. Long before the sun becomes a red giant and literally expands to engulf the inner solar system, that Earth's surface will have become as hostile to life as Venus is today. This is not a matter of speculation. It is the expected end of Earth as a living world, based on stellar physics, that is about as well understood as any physics gets. This means that if life on Earth, and whatever civilizations emerge from it, wants to persist beyond a certain time scale, it will eventually need to leave. Not because of any catastrophe, not because humanity destroyed itself, not because an asteroid hit or a supervolcano erupted, but because the sun will, in its gradual way, become too much. Earth's habitability has an expiration date, and the date is measured in billions of years. Not billions of years from now, but still finite, still an expiration, and the only way past it is up. This is, in the most essential way, why interstellar travel matters. And not for tourism, not for exploration in the casual sense, but as the ultimate insurance policy, as the only possible answer to the question of long-term survival. Every civilization that does not solve the problem of interstellar travel is, on a long enough timescale, a civilization with an expiration date, which is uncomfortable to think about, but which has the virtue, at least, of being honest. There is a concept among space enthusiasts and futurists sometimes called the Great Filter, popularized by the physicist Enrico Fermi's famous question about why we haven't detected any signs of extraterrestrial intelligence. If the universe is as old and as large as it is, and if planets like Earth are as common as they appear to be, and if life arises as easily as it apparently did on Earth, then where are all the civilizations? Why is the sky not full of signals and spacecraft and evidence of intelligent activity? One answer, not the only one, but a genuinely chilling one, is that there is some step in the development of civilizations that is extraordinarily difficult. Some barrier so high that almost no one gets past it. And one candidate for that barrier is exactly this: the ability to leave your home system before it becomes uninhabitable. The ability to solve the interstellar travel problem before the need becomes urgent. To become a multistellar species before you run out of your own star's patience. If that's the barrier, then the silence of the cosmos might be the sound of failure. Billions of civilizations rising and thriving and reaching for the stars and hitting that wall and falling back. Not in war or catastrophe, but simply because the distance was too great. Because the physics was too hard. Because the time required exceeded the civilization's duration. The stars weren't taken. They were just too far. And the civilizations of the past just quietly faded when their windows closed. This is not a comfortable thought. It is not supposed to be. It is the kind of thought that lives in the back of your mind on clear nights when the stars are out and the air is still, when you stand in the dark and look up and feel that particular loneliness that is not really loneliness at all, but something bigger. The awareness of scale, the awareness of time, the awareness that all of this, the cities, the languages, the art and the science and the love and the grief, had all the accumulated weight of human experience, is taking place on a speck of rock orbiting an ordinary star in the outskirts of a galaxy that contains 400 billion other stars, and that outside the thin shell of this planet's atmosphere, the universe is indifferent in a way that is very hard to be comfortable with. But there is another way to sit with this feeling. There is a version of this story that is not about limitation or failure or the cold indifference of physics. It is about the astonishing, almost improbable fact that it is possible to think about it at all. That somewhere on the surface of this planet, biological machines made of water and carbon and several dozen other elements have assembled themselves into systems capable of wondering about the distance to the nearest star, of calculating it, of naming it, and of being troubled by it, of lying awake at night with the weight of it pressing gently on the chest. The universe did not have to produce anything capable of asking these questions, and yet here we are, asking them. And the asking matters, because it is how things change. The history of human technology is not primarily a story of things being possible in advance. It is mostly a story of things being impossible for a very long time, and then becoming possible because someone spent long enough asking the question seriously. The distance to the moon was impossible. The polio vaccine was impossible. The internet was impossible. Every major transformation in human capability began with someone confronting an impossibility and deciding to spend their life not accepting it. The interstellar problem is harder than any of those. Much harder. Harder by orders of magnitude. But it is not impossible in the way that logical contradictions are impossible. The laws of physics don't forbid it. They make it very hard. And very hard and impossible are not the same thing. The story of Proxima Centauri b began, oddly enough, not in 2016 but much earlier. The star itself has been known since 1915, when Robert Innes, a Scottish astronomer working in South Africa, noticed that a dim red star near Alpha Centauri had an unusually large proper motion. It was moving across the sky faster than almost any other star. This motion, a reflection of its proximity to Earth, led to the recognition that it was the nearest star to the Sun. Innes named it Proxima Centauri, Proxima being Latin for nearest. For decades, it was a mere fact. The nearest star. No particular significance beyond that. And it sat in the sky of the southern hemisphere, invisible to the naked eye, a faint red ember in the constellation Centaurus. Astronomers knew it was there. It appeared in textbooks. It was cited in discussions of interstellar travel as the obvious first destination. But it was a destination without a reason, without a why, without anything to suggest it was special beyond its proximity. The discovery of Proxima b changed that. The discovery came from a long, careful analysis of the star's radial velocity, its motion toward and away from Earth, measured by the Doppler shift in its light, the same phenomenon that makes a siren change pitch as an ambulance passes. A planet orbiting a star will cause the star to wobble very slightly, moved by the planet's gravity in a tiny but detectable cycle. The amplitude of this wobble and its period, and I tell you the planet's mass and orbital period. The team of astronomers who found Proxima b, an international collaboration that spent years carefully teasing the signal out of the noise, announced their discovery in August 2016 in the journal Nature. The planet completed one orbit of Proxima Centauri every 11.2 days, suggesting it received about 65% of the energy that Earth receives from the Sun, placing it, given the much dimmer nature of Proxima Centauri compared to our Sun, squarely in the habitable zone. Its mass was estimated at roughly 1.3 times Earth's mass. It was rocky. It was there. The reaction was immediate and global. Every major newspaper covered it. Social media lit up. And scientists who study astrobiology found themselves fielding calls from journalists and politicians and members of the public who all wanted to know the same thing. Is there life there? The scientists were understandably cautious. We don't know, they said. We can't see the atmosphere. We don't know about the magnetic field. The flares are a concern. It might be habitable. It might not be. We need more data, which was all true, which was all the honest, scientific answer. But the public heard it differently. The public heard there might be life there, which, given that Proxima b is the nearest, potentially habitable world ever found, and given what that means in terms of the long questions of humanity's place in the cosmos, was not an unreasonable response. Several follow-up studies have since complicated the picture. A 2020 study suggested there might be a second planet in the system, farther out, though this has not been confirmed. Another study attempted to characterize the atmospheric conditions using data from the Hubble Space Telescope, and found tentative evidence that large flares had stripped away significant atmosphere, though interpreting this data is tricky. More recently, the James Webb Space Telescope, humanity's most powerful space observatory, launched in 2021, has been gathering data that may eventually tell us something definitive about the atmospheres of nearby exoplanets, including those in the Proxima Centauri system. But eventually, in this context, may mean years of patient observation and careful analysis. What we can say with confidence is that Proxima b exists, that it orbits in or near the habitable zone, that it is roughly Earth-sized, and that it is, by an enormous margin, the nearest such world to our own. Everything else remains, for now, open. There is a concept in philosophy and cognitive science called the overview effect, named for the profound perceptual shift that astronauts report when they first see the Earth from space. The smallness of it, the fragility of the thin blue atmosphere, the complete absence of any visible borders, any sign of the conflicts and divisions that consume so much human attention on the surface. The feeling, described consistently by people of very different backgrounds and personalities and nationalities, of seeing their home as a single, whole, impossibly precious thing. Not a collection of countries and cultures and interests, a whole, a single object, delicate and beautiful and lonely, floating in the void. Many astronauts describe this experience as transformative in a way that is difficult to articulate. It doesn't just change how they think about Earth. It changes how they think about themselves, about their place in things, about what matters and what doesn't, about the strangeness and the privilege of being a conscious being in a universe that has no obligation to contain consciousness at all. Several have come home and made significant changes to their lives, their priorities, their work. Several have written about it extensively. Almost all of them say that no photograph can capture it, that the experience is fundamentally embodied, that you have to be there, floating in that void, with that view, for the feeling to land properly. And I wonder what the equivalent of the overview effect would be for an interstellar crew. What it would feel like to look back and see nothing. To have traveled so far that even the sun, which has been the center of human existence since the first humans looked up in wonder, has shrunk to just another star. Just one of many in a sky full of stars. The feeling of leaving everything, completely, with no way back. Of being the first creatures of Earth to exist entirely outside any sun's direct influence. In the true deep of interstellar space, would it be terrifying, peaceful, both at once? Would it produce a kind of clarity, the same clarity the astronauts describe, but deeper, more absolute, earned through a greater extremity? Or would it produce something else, something that has no name yet, because no human being has ever been there to feel it? These are questions that only time and unimaginable technical achievement and perhaps a kind of courage that the world hasn't yet produced in sufficient quantities can answer. But they are not idle questions. They matter, because the stars are there, and they are not waiting for us. They do not care whether we come or stay. The distance is what it is, and the physics is what it is, and the universe is indifferent in that beautiful and terrible way it has always been. But we are not indifferent. We are the thing that looks, the thing that wonders, the thing that measures the distance and feels the weight of it, and then asks, against all reason, whether there is a way. Let's talk about what would actually need to happen, not in the abstract, and not in the sweep of centuries and civilizations, but concretely. What would need to change in the world we live in today for interstellar travel to become possible? This is not a small question, and it doesn't have a simple answer, but it's worth trying to sketch the shape of it. The first thing that would need to change is energy. The fundamental limit of all current propulsion systems is not cleverness or design. It is energy. We don't have enough of it in concentrated enough forms to drive a spacecraft to interstellar speeds. Every serious proposal for interstellar travel, every one of them, without exception, requires an energy source far beyond what current technology provides. Nuclear fusion, if it can be made practical, would help enormously, not solve the problem, but help. Not solve a practical fusion reactor would provide a power density and efficiency that is orders of magnitude better than chemical combustion, and the fuel, hydrogen or helium, is among the most abundant elements in the universe. A fusion-powered spacecraft might not reach 5 or 10% of the speed of light, but it could reach fractions of a percent that make interstellar travel timescales measured in centuries rather than millennia. Which is still not a human lifetime. But it's something. It's a first step rather than a closed door. The second thing is materials science. Reaching high fractions of the speed of light requires that the spacecraft not be torn apart by the physical environment it's passing through. The interstellar medium, though extremely sparse, is not empty. At 1 to 10% of the speed of light, even a microscopic grain of dust, which might weigh only a few micrograms, hits the spacecraft with the energy of a rifle bullet. A spacecraft cruising at those speeds through the interstellar medium would be hit by hundreds of these impacts every second. The leading edge of the spacecraft would need to be made of materials that are simultaneously extremely hard, extremely light, and capable of either deflecting or absorbing these impacts without catastrophic failure. No such material currently exists. But materials science is advancing at extraordinary speed, driven by entirely different applications: computing, medical devices, structural engineering, and the materials of the future may have properties that are difficult to imagine from where we stand today. The third thing is information technology. For many of the more exotic interstellar proposals, including Breakthrough Starshot's gram-scale chip, the key challenge is packing enough sensing and computing capability into a vanishingly small package and then getting the data collected over years of travel transmitted back across light years of space using minimal power. This is a challenge that is genuinely in the domain of ongoing technology development rather than physics fiction. Computing power has been improving for decades. Sensor miniaturization has been improving for decades. Directed energy communication, lasers, rather than radio waves, can send more data with less power across greater distances. The computing challenge of an interstellar probe, while formidable, is perhaps the most tractable of all the challenges, in the sense that it tracks most naturally with the direction technology is already moving. The fourth thing, and this is the one that is hardest to talk about because it's not technical at all, is time. Not travel time, institutional time, civilizational time. The time it takes a species to build the kind of infrastructure and accumulate the kind of knowledge and develop the kind of patience and sustained commitment that interstellar travel actually requires. The Apollo program, which sent humans to the moon, took about 10 years, from conception to first landing. The International Space Station took about 30 years, from initial planning to its current configuration. The Large Hadron Collider, the most complex scientific instrument ever built, took about 20 years to design and construct. And a practical interstellar mission, even the minimal robotic version, would likely require sustained international effort over a period of decades to centuries. Not a sprint, but a marathon that spans generations. Not a program of one country or one era, but a project of humanity as a whole, sustained through changes in government and culture and priority and understanding. History suggests that humans are not especially good at this. We are excellent sprinters. We are capable of extraordinary collective effort over periods of years or a decade when there is a clear, visible goal and a competitive or existential pressure. The Apollo program happened because of the Cold War, because of a specific competitive pressure at a specific moment that made the moon race urgent in a way that ordinary science never is. The Large Hadron Collider happened because of a generation of particle physicists who shared a vision and convinced enough governments to fund it across enough decades. Interstellar travel would require something like that, but sustained not for a decade, not for a generation, but possibly for centuries, with no clear competitive pressure, with no immediate existential threat, with many competing priorities and limited resources and the normal entropy of human institutions and human attention. This is perhaps the deepest challenge. Not the physics, not the engineering, not even the biology. The challenge of maintaining collective purpose across timescales that exceed human memory, in service of a goal that will deliver no payoff to any of the people who make the early sacrifices. The challenge of saying, we begin this now, and knowing that our great-great-grandchildren will be the ones who finish it and find it to be worth it. There is something beautiful about this problem if you look at it in a certain way. Not beautiful in spite of its difficulty. Beautiful because of it. Because the problem of interstellar travel, of reaching even the nearest star, is fundamentally a problem about the relationship between human ambition and physical reality. It is the clearest possible test of whether the gap between what we want to do and what the universe allows is bridgeable. And unlike most of the important problems that face humanity today, which are social problems, political problems, problems of will and organization and collective action, interstellar travel is a problem where nature is the adversary, not other humans, not human institutions or human history or human self-interest. The laws of physics, the geometry of space, the coldness of the void, these are adversaries that do not compromise, do not negotiate, cannot be lobbied or influenced or appealed to. They simply are. And the challenge is to find a way within them. This is, in a strange way, clarifying. The solutions to interstellar travel, if they come, will come, because of deep understanding of how the universe works, combined with extraordinarily creative engineering, combined with sustained human commitment. Not because of politics, not because of ideology, not because of economics, though all of these will play a role, but fundamentally because the laws of physics were understood and worked with, rather than wished away. There's something almost like respect in that. Respect for the difficulty, respect for the adversary. The universe is not hostile to us, but it is indifferent, and working within that indifference, finding the narrow paths that physics allows. That is a kind of beauty. Now I want to tell you something about the red dwarf star at the center of all this. Something that is not usually in the conversation about interstellar travel, but which feels important, something that has to do with time, and with the strange longevity of small things. Proxima Centauri is, as I mentioned, a red dwarf, the smallest stable type of star. Cool, dim, slow burning. It produces about 1.5 thousandths of the sun's luminosity, a dim red ember in the dark, and it will burn, slowly, steadily, almost incomprehensibly slowly for about 4 trillion years. Yet the universe is currently about 13.8 billion years old. In 13.8 billion years, the universe has gone from the hot, dense plasma of the Big Bang to the current state of things, hundreds of billions of galaxies, each containing hundreds of billions of stars, some with planets, some of those planets harboring life, one of them harboring us. All of that in 13.8 billion years. Proxima Centauri will burn for 4 trillion years. That is about 290 times the current age of the universe. If the universe were a single year, and we are living through it in the first 2.5 weeks of January, Proxima Centauri will still be burning in late October. Everything else, all the large stars, the medium stars, even stars like our sun, will be cold and dark. Most galaxies will have lost their gas reserves and stopped forming stars. The night sky, for anyone alive to see it in that far future, would be mostly dark, lit only by the last few red dwarfs still slowly burning, and Proxima Centauri would be one of them. Still going, still warming Proxima b. If it still exists, if it still has an atmosphere, if there is still something there to be warmed. In a universe that grows increasingly dark and cold with time, the red dwarfs are the last campfires, and Proxima Centauri, our nearest neighbor, the destination of our highest interstellar ambitions, is one of those last fires. It is possible to feel something about this, not just to think about it, but to feel it. The image of this small, dim star, invisible to the naked eye, irrelevant in photographs, overshadowed in brightness by its brighter neighbors, quietly outlasting everything else in the observable universe. Still going, and billions of years after the sun has cooled, still radiating its faint warmth into a sky full of nothing. There is something about that, something that resists easy description. The question this story keeps circling back to is not really a technical one. It's an emotional one, maybe a spiritual one, if that word doesn't make you uncomfortable. It is this: what kind of relationship do we want to have with the universe we find ourselves in? We did not ask to be here. No one does. We arrived in this universe without orientation, without instructions, without any guarantee of meaning or purpose or continuity. We are, as far as we know, a temporary arrangement of matter that has developed the unusual property of being aware of itself of being able to look up at the stars and understand at least partly what they are, and of being able to reach for things beyond immediate reach. This is not nothing. In a universe as old and as large as this one, the emergence of anything that can wonder about itself is extraordinary. And what we do with that wondering, how we respond to the enormity of the universe and the smallness of our position in it, is one of the most important questions we face. There is one response that says, the universe is too large, the distances too great, the obstacles too severe. Let us tend to our own garden. Let us solve the problems on the planet we have before reaching for planets we may never see. This is a reasonable response. It is not wrong. The problems on the planet we have are real and urgent, and require all the intelligence and attention we can bring to bear on them. And the resources needed for interstellar travel, the energy, the materials, the engineering capability, could also be applied to problems of immediate human need. This tension is real, and it doesn't resolve easily. But there is another response. One that says, the universe does not wait for us to be ready. The questions do not wait for us to be comfortable. The stars are there now, and they will be there whether or not we go. But whether or not we go says something about us, about the kind of beings we are or are trying to become, about whether we are content to be the curious ones who look but do not move, or whether we choose to be the ones who try. Because here is the thing about impossibility. The grain of sand that represents our solar system on a scale model of the Milky Way, it is impossibly small. The energy required to reach even a fraction of the speed of light is impossibly large. The time required, even with the best technology we can imagine, is impossibly long by human standards. The engineering challenges are impossibly complex. The biology is impossibly fragile. And yet, we know Proxima Centauri b is there. We can detect the slight wobble its gravity puts into the motion of its star from 4 light-years away. We can measure the period of its orbit and estimate its mass and locate its position in the habitable zone of its star. We can do that with instruments on the surface of this planet. From here, we can reach, at least with understanding, 4 light-years into the dark and find a world. That is not nothing. That is a start. That is the first step of a journey whose later steps we cannot yet imagine, but whose direction is clear. I want to close this part of the story with something that is not about engines or radiation or generation ships or the impossible math of the rocket equation. Something smaller. Something more personal. There's a photograph taken by the Voyager 1 spacecraft in 1990. The spacecraft, then about 3.7 billion miles from Earth, was commanded by astronomer Carl Sagan to turn its camera back toward the inner solar system. The resulting image shows Earth as a tiny point of light, what Sagan called the pale blue dot. In the photograph, Earth takes up less than a pixel. It is smaller than a dust mote, lost in the immensity of space, barely distinguishable from the noise in the image. And yet it is everything. Every human being who ever lived, every civilization, every act of love or cruelty or genius or stupidity, the entirety of human experience, all of it happened on that pale blue dot, on that single pixel of light in an image full of darkness. Sagan wrote about this image. He wrote words that have been quoted many times since, and that still land with the same weight each time. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit, yes. Settle, not yet. Not yet. He wrote not yet, not never, not impossible, not forever beyond reach, not yet. There is a whole universe of possibility in those 2 small words. And maybe that's the most honest thing that can be said about this, that the stars are too far for us now, that the gap between where we are and where the stars are is, at this moment in the story, too wide to cross, that the challenges are real and severe and not to be minimized, that the physics is unforgiving and the biology is fragile and the psychology is complicated and the ethics are genuinely difficult. All of that is true. And also, not yet. Think about the night sky for a moment. Not as an astronomer, not as an engineer, just as a human being, standing on the surface of a planet, looking up. The stars you see are not where they appear to be. The light reaching your eyes left those stars years, decades, centuries, millennia ago. When you look at the Andromeda Galaxy, visible to the naked eye as a faint smudge in the northern sky, you are seeing light that left it 2.5 million years ago. Before our species existed, the light traveled for 2.5 million years through the void between galaxies and landed on your retina right now. In this moment, you are looking at the past. The ancient light of something impossibly far away has traveled through the universe specifically to enter your eyes. This is not a metaphor. This is physics. And it means that when you look at Proxima Centauri, which you could, with a telescope, from the southern hemisphere, you are seeing it as it was 4.24 years ago. The light that left it then has been traveling through the void since then and is now at Earth. A tiny part of it is entering your eye. And a photon that bounced off or was emitted by a star 25 trillion miles away is completing its journey at your retina. There is something intimate about this, something that defies the cold arithmetic of the distance. The universe has connected that star to you through the medium of light, across an almost incomprehensible void, in a way that cost nothing and required no technology. We are already in contact with the nearest star, not the way we dream about, not with a probe, not with a crew, not with the ability to answer questions or receive answers, but in the only way the universe currently allows: light, photons, the fundamental particles that carry information across the void at the maximum speed physics permits. Proxima Centauri's light is here. It reaches Earth every moment. How it falls on the deserts and the oceans and the faces of anyone who stands outside on a clear night in the southern hemisphere and looks toward the constellation Centaurus. The star is 25 trillion miles away, and its light is here. That connection exists. It is real. It is not enough. But it is something, and it matters, and it points toward a more complete connection that might, across the long arc of whatever comes next for this species, eventually be possible. Here is a lesser-known fact about interstellar travel that sometimes surfaces in the corners of physics discussions and tends to stop conversations in an interesting way. It has to do with the nature of space itself. For most of the history of space exploration, for all of it really, until very recently, we have thought of space as a backdrop, a stage on which things move. As stars and planets and spacecraft and galaxies moving through space, which is simply the empty container that holds them. This is the everyday, intuitive picture of space. An infinite three-dimensional arena, the same in every direction, waiting to be crossed. But Einstein showed us something deeper. Space is not a static backdrop. It is dynamic. It can stretch, curve, vibrate. And general relativity, Einstein's theory of gravity, contains within it a mathematical structure that, under certain conditions, might allow for something that sounds impossibly like a shortcut. The Alcubierre drive, proposed by the theoretical physicist Miguel Alcubierre in 1994, describes a mechanism by which space itself around a spacecraft could be warped, contracted in front of the vessel, and expanded behind it, so that the vessel essentially surfs a wave of space-time. The vessel itself would not be moving through space faster than light. It would be stationary relative to its local space-time. But the space-time containing it would be moving, and there is nothing in relativity that prohibits space-time from moving faster than light. Space-time does not itself have a speed limit. Only things moving through space-time do. The Alcubierre drive remains entirely theoretical. The energy required to produce the required space-time distortion, under the original formulation of the idea, was equivalent to the mass energy of a planet the size of Jupiter, converted entirely to exotic negative energy, a form of energy that may not exist in sufficient quantities to be useful. Various refinements of the idea have reduced this requirement, but even the most optimistic contemporary analyses require exotic physics. Forms of energy with negative pressure, hypothetically possible in certain quantum field configurations, but entirely beyond current experimental reach. The Alcubierre drive is not a technology. It is a mathematical curiosity, a solution to Einstein's equations that shows that such a thing is geometrically allowed, without saying anything about whether it is physically achievable. But it matters, in a subtle way, because it shows that the universe's rules, properly understood, do not explicitly forbid shortcuts. They make shortcuts extraordinarily difficult. They require things that may not be achievable, but they don't draw a clear line and write absolutely not on the other side of it. The universe leaves a door, very heavy, very stuck, with no obvious way to open it. But a door, not a wall. And that distinction, even if it amounts to almost nothing in practical terms today, is the kind of thing that sits in the mind and refuses to be dismissed entirely. There is one more thing I want to say about the physics before we move deeper into the human dimensions of this question. It is about a concept that is genuinely one of the strangest and most beautiful ideas in all of science, and it has direct implications for interstellar travel in a way that is often overlooked. It's called time dilation. Einstein's theory of special relativity tells us that time does not pass at the same rate for everyone. It depends on velocity. Yet the faster you move relative to a given reference frame, the slower your own time passes compared to that reference frame. This is not a philosophical statement. It is an experimentally verified fact. Atomic clocks on fast-moving airplanes run slightly slower than identical clocks on the ground. GPS satellites, which move at significant speeds relative to Earth's surface, have to account for relativistic time dilation in their programming, or the navigation system would drift by several miles per day. The effect is tiny at the speeds of everyday life, and even at the speeds of airplanes and satellites. But as you approach the speed of light, the effect becomes enormous. If you were traveling at 99% of the speed of light, time dilation would mean that for every year that passed on Earth, only about 2.5 months would pass for you on board the spacecraft. At 99.9% of the speed of light, for every year on Earth, less than 2 weeks would pass for you. As you approach ever closer to the speed of light, the ratio becomes more and more extreme, until at the limit, at exactly the speed of light itself, which massive objects can never reach, time would stop entirely for the traveler. In principle, at extremely high fractions of the speed of light, you could cross the entire Milky Way in a human lifetime, even though hundreds of thousands of years would pass on Earth during your journey. This is real physics. It is not speculation. It is as well established as any physical fact we know. Yes, and it means that the interstellar distances that seem so insuperable are not necessarily absolute limits on human travel. They are absolute limits on the travel time, as experienced by Earth. For the traveler, moving fast enough, the subjective journey time could be much shorter. The trip to Proxima Centauri at 99% of light speed would take about 4.3 years, as measured by Earth. But the crew would experience only about 7.5 months. At higher speeds, the traveler's experience of the journey time shrinks even further. Of course, reaching 99% of the speed of light requires energy that makes our earlier calculations about 10% of light speed look modest. The energy requirements at relativistic speeds become staggeringly large. And the collision problem, the impact of interstellar dust at those speeds, becomes catastrophic. These are not small obstacles. But time dilation at least opens a philosophical window. The distances to the stars are not fixed walls for a traveler. They are walls whose height depends on how fast you can go. And for a being that could travel at 90 or 95 or 99% of light speed, which requires solving enormous engineering problems but not breaking any physical laws, the galaxy becomes, in a strange way, smaller. Let us think about something quieter now. Something that doesn't require math or physics or engineering. Something that requires only the imagination, which is always here, which costs nothing, which is possibly the most important tool we have for everything that matters. Imagine that it is the year 2300. Not an outlandish future, not a science fiction future of flying cars and alien civilizations and human beings living on 100 worlds, just 280 years from now. About as far from us as the United States is from its own founding. As far as we are from the midpoint of the Enlightenment. A very modest distance in historical time. In 2300, there is a spacecraft. It is large, much larger than anything built before. It carries a crew of perhaps 20 or 30 human beings, and it is moving. Not fast by the standards of light, but fast by the standards of anything human beings have built. Maybe 1% of the speed of light, maybe 2. Fast enough that, barring any disasters, it will reach Proxima Centauri in a few centuries. The people on board are not the same as the people who built it. And that ship was launched sometime in the 22s. The builders are gone. Their children perhaps are also gone. The people on board were born on the ship. They grew up in its corridors, went to school in its classrooms, worked in its gardens, fell in love in its recreation areas. They have never set foot on Earth. They have never felt sunlight on their skin. Not real sunlight, the sunlight of a star you are orbiting, but the artificial light of the ship. They have read about Earth, studied it. The memories of it are part of their culture, part of their mythology. Earth is the origin place, the home that was left behind, and they carry it the way all diaspora peoples carry their origins, in stories, in recipes, as in ceremonies that have evolved and changed over generations, until they resemble their Earth sources in the way that all traditions resemble their origins, recognizably, but differently, and they are almost there. Not quite. Maybe a generation away. The instruments are showing stellar parallax of Proxima Centauri that is different from what it looked like from Earth. The star is close enough now that its position in the sky shifts measurably as the spacecraft moves. They are within a light year, maybe less. And Proxima Centauri in the forward-facing telescope is no longer a dot. It has a disk. Faint and red and small, but a disk. An object with an apparent size. A star they can almost see. And Proxima b, their destination, or the object that the original mission was designed to reach, is theoretically visible in the most powerful instruments on board, not as a world, not as a place, as a point of light near the star, a pixel of reflected light, but a specific pixel, their pixel. How would they feel? These people who were born here, who have known nothing but this ship and these corridors and these people and the stars outside the windows. How would they feel, looking at that faint red star growing slowly larger? What would the weight of that approach feel like? The awareness that they are completing something that began generations ago, something that cost the lives of people they never knew, something that was built on a chain of sacrifice and commitment stretching back across centuries to a world they have never seen. I don't know. Nobody knows. We have never been in that position. The closest analogs in human history, the first humans to arrive at a new continent perhaps, or the descendants of enslaved people who eventually reached freedom, are far from adequate comparisons. This would be genuinely unprecedented. The first human beings to approach a star other than our own sun. The first to see the disk of a sun that was not their birth sun growing larger in the windows. The first to enter the gravitational embrace of another star. That moment is not in any history book. It hasn't happened yet. But it could. It might. Someday. If everything goes right. If the problems yield. If the commitment holds across the generations. There is a thought that I keep coming back to, and I want to share it, even though it is difficult to express without sounding either grandiose or naive. It is this. The problem of interstellar travel is not really a problem about space. It is a problem about time, not travel time, though that is part of it. But the deep civilizational time it takes to go from "this is impossible" to "this is being done." The time it takes a species to accumulate enough knowledge, enough capability, enough sustained collective will to do something that was impossible for all its previous history. This is a kind of time that doesn't obey the normal rules of urgency. You can't rush it, you can't throw money at it and have it arrive faster. It requires the slow accumulation of generations of work, each building on what came before, and each solving one piece of a puzzle so large that no single generation can see all of it. This is the timescale of cathedrals, of languages, of civilizations themselves. We are, in the history of the problem of interstellar travel, very early. The first people who seriously did the math on what it would take, the Tsiolkovskys and the Goddards and the people at the British Interplanetary Society who wrote the Daedalus Report in the 1970s, were laying the foundations of a cathedral that will take centuries to build. We, today, are perhaps a little further along. Breakthrough Starshot is another stone in the wall. The James Webb Space Telescope telling us what Proxima B's atmosphere might contain is another stone. Every paper on fusion propulsion, every study of long-duration human spaceflight, and every analysis of the psychological challenges of isolation. Each of these is one more stone. The cathedral is rising, slowly, but it is rising, and the generations that come after us will be standing on what we have built, seeing further because of it, adding their own stones. And at some point, not soon, but not never, the work will be done, and someone will fly. Here's something that often goes unsaid in the interstellar travel debate. The act of trying matters independently of the outcome. The work done in service of interstellar travel has produced, and will continue to produce, technologies and understanding with immediate applications to human life on Earth. Nuclear fusion research, driven partly by the dream of space applications, is also the most promising path to clean. Abundant energy for a civilization struggling with climate change. Advanced materials developed for spacecraft might become the structural materials of tomorrow's buildings, vehicles, and medical devices. Closed-loop life support systems, developed for interstellar missions, would be directly applicable to building sustainable habitats on Earth, or in space, in ways that could matter a great deal in the coming centuries. Miniaturized computing systems designed for interstellar probes push the boundaries of what is possible in electronics and computing generally. The attempt to do something this hard always yields more than the thing itself. And then there is the less tangible benefit, the effect on human consciousness of keeping this question alive, of insisting generation after generation that the stars are not forever beyond reach, of maintaining the aspiration. There is something important about the way a civilization thinks about its own future, about whether the story it tells itself is one of expansion or contraction, of opening or closing, of possibility or inevitability. The civilizations that reached for the stars, even just metaphorically, even just in the imaginations of their writers and scientists and dreamers, have tended to be different kinds of civilizations from the ones that didn't. More curious, more willing to invest in basic knowledge, more comfortable with uncertainty, and with the long timescales of genuine discovery. Whether this is cause or effect or both is difficult to say, but the correlation is real. We are reaching the end of this particular stretch of the story. Not the end of the question doesn't end. And it sits there in the dark, patient and enormous, like the stars themselves, but the part we've been exploring together, the part that runs from the misleading word just, in just 4.24 light years, through the physics and the engineering and the biology and the ethics and the psychology and the philosophy and the longing, that part is coming to a close. And I want to end it, not with a conclusion, because there is no conclusion here. Not with a summary, because the summary would not do it justice. I want to end it with the image I started with, the grain of sand, the pale blue dot, the way that an ordinary evening, with the sky clear and the air still, and the world doing all the ordinary things worlds do, can produce a moment of looking up, of noticing, of the stars, which are always there and which we mostly ignore because there are always other things to attend to, suddenly being visible, being real, being enormous and close and distant all at once. The nearest star is 4.24 light-years away, 25 trillion miles, a distance that swallows every human timescale, every human speed, every human notion of nearness, a distance that makes the fastest thing we have ever built seem like a stone dropped into the ocean and watched until it disappears. And within that distance, sitting in the darkness of the void, orbiting a dim red coal of a star that will outlive the universe, there is a world, a rocky, possibly Earth-sized, possibly water-bearing world, whose surface we cannot see, whose atmosphere we cannot measure, whose nature we do not know, whose loneliness or richness or emptiness is as yet undetermined, a world that might, in all its mystery, be alive. We cannot get to it, not yet, not with anything we have built, not in any time scale that a human being, or a generation, or a century of generations can contain. The distance is real, and the obstacles are real, and the physics is unforgiving, and the universe is indifferent. All of this is true. And also, the light from that star is here, right now. It has been traveling for 4.24 years through the void, and it has arrived. It is falling on the southern hemisphere of Earth, every second of every day, available to anyone who looks. The connection is already there, made of light, made of information traveling at the maximum speed physics allows. The star is speaking, in the only language the universe provides. And we are, in our way, listening, looking up, wondering. That is where we are. In the long, humbling, impossible, irreplaceable middle of a story whose beginning was the first time a human looked up and wondered about the lights in the sky, and whose end, if it has one, is somewhere we cannot yet see. But we are in it. We are the part of the universe that is conscious of the problem. And being conscious of it, being troubled by it, being moved by it enough to think about it in the quiet hours of the night, that is not a small thing. That might be the most important thing. The closest star is 4.24 light-years away, and we are going to keep looking at it, keep measuring it, keep dreaming about it, keep working toward it, for as long as there are human beings capable of looking up, because the looking is not separate from the going. Yet the looking is how the going begins, and we are only at the beginning. Spend any amount of time reading about the actual proposals that have been made for reaching Proxima Centauri, and you will notice something. Something that starts as a small observation and grows into a kind of profound respect for the people doing this work. The proposals are not naive. They are not wishful. The scientists and engineers who work seriously on interstellar travel are among the most rigorous and unsentimental people in any field. They are not ignoring the obstacles. They are making careful, detailed lists of them. They are calculating the energy requirements with brutal precision. They are writing papers about the structural failure modes of gram-scale probes traveling at relativistic speeds, and about the psychological deterioration timelines of isolated crews, about the thermodynamics of closed-loop life support systems. They are doing the real work, and the real work, right now, mostly confirms how hard this is, how far away the solution is, how many problems remain unsolved, and how deep those problems run. And yet, they keep going. They keep writing the papers, running the calculations, attending the conferences, building the organizations. They keep Breakthrough Starshot alive. They keep publishing the fusion drive designs, even though fusion isn't solved. They keep studying the biology of hibernation, even though human torpor is decades away. They keep sending the telescopes that study Proxima Centauri B's star and its radiation environment, building the knowledge base that any future mission would require. Yet they do this knowing that they will not live to see the result, knowing that the payoff, if it comes, is centuries away, knowing that the skeptics are not wrong, the obstacles are real, the timeline is long, the outcome is uncertain. Why? This is a genuine question, not rhetorical. Why do serious, brilliant, unsentimental people devote their careers to a problem that they know will not be solved in their lifetimes? The answer, as best as I can understand it from reading their work and listening to them talk about it, is something like this. Because someone has to. Because the problem is real, And real problems don't go away by being ignored, because every generation that makes progress on this problem, even small progress, even understanding one more piece of the puzzle, leaves the next generation closer to the goal. Because the alternative is to not try, and not trying is its own kind of answer to the question of what kind of species we are. And because there is something in the problem itself, in the encounter with a challenge this hard and this important, that is intrinsically worth doing, that produces understanding and capability and knowledge as byproducts even when the main product is still not finished. That is, in the most fundamental sense, what science and engineering and human curiosity are for. The universe is about 13.8 billion years old. In those 13.8 billion years, it has produced, as far as we know, exactly one species capable of asking whether it can reach the stars. One species, on one planet, around one ordinary star, in one unremarkable corner of one galaxy among hundreds of billions. And that species has been capable of this question for perhaps 100,000 years, perhaps less. A blink of time, cosmologically speaking. A fraction of a fraction of a fraction of the age of everything. In that blink, we have gone from having no technology at all to having technology capable of landing robots on Mars. We have mapped the genome. We have built computers that can process information at speeds incomprehensible to the human mind. We have discovered the structure of the universe, the age of the stars, the nature of black holes, the existence of other worlds. We have done all of this in a moment of cosmic time so brief that it barely registers. And we are just beginning. The curve of capability is steep. The things that seem impossible today are the baseline of some future century's ordinary achievements. The gap between now and what would be needed for interstellar travel is large, but it has been closing, slowly and unevenly but steadily, for as long as humans have been curious about the sky. Proxima Centauri b is there, 4.24 light-years away, orbiting its small red star every 11 days, receiving its portion of red light and occasional lethal radiation. Its surface, whatever it looks like, is there right now. Maybe rock and ice and ancient craters, like a quieter version of the moon. Maybe something else. Something with liquid water and sheltered valleys. Something with chemistry approaching complexity. Something with weather patterns and atmospheric cycles and the slow, patient work of geology. Maybe not. Maybe empty. Maybe alive. We don't know, but we will look. That much is certain. We will point better telescopes at it. We will gather more photons that have traveled 4 light-years to reach our instruments. We will learn what we can learn from here, using the only tools we have for now, which is the light the universe sends us and the intelligence we use to read it. And we will think about how to go further, how to send something, a chip, a probe, eventually a crew, across that void. Not because it is easy, but because it is there, and because we are the creatures who look and wonder and reach. The distance is real. 25 trillion miles of cold, silent, radiation-filled void, with no way stations and no shortcuts and no forgiveness for failure. The physics is unforgiving. The biology is fragile. The engineering challenges are immense. The timescales are humbling. All of this is true. And also the star is beautiful, red and small and patient, burning at the edge of the southern sky, 4 light-years away. Its light is here. We are already in contact, in the only way the universe currently allows. And that is, perhaps, enough. For now. For this moment in the story. Enough to stand outside on a clear night and look south, toward Centaurus, toward the dim red star that might have a world, and feel the weight of the distance, and the weight of what it would mean to cross it, and the quiet, persistent, very human possibility of yes, not yet, but not never, not yet, but not never. The closest star may be too far for us today, but tomorrow is a long time, and we are stubborn creatures, and we have not yet stopped looking up.